Okay, so we are on lecture, I think it's labeled 6.3, but we can look at this as chapter 5, number 2, on more chemical reactions. Specifically, this is going to be on acid-base reactions and precipitation reactions. So acid-base reactions and precipitation reactions are both ways of classifying reactions, just like we've been doing classifying reactions, but these are specialized versions of our double displacement reactions. So again, our double displacement reactions have the formula AB plus CD goes to form AD plus CB. Now we talked about how it has to follow exactly this formula because these happen with ionic compounds. Cations are always listed before anions. So the cation from the first compound will only be attracted to the anion from the second compound. Cation from the second compound will only be attracted to the anion from the first compound. And since cations are always listed first, that's why we end up with the cation C being listed before the anion B rather than vice versa. So that's how they end up together. Now, it's not always +1 and -1, but you can see how the positively charged ion, whatever the value is, ends up being attracted to the negatively charged ion. Any questions on that before we look at how that specifically applies to acid, base, and precipitation reactions? Or if you're with me, say, I'm with ya. Excellent. Okay. Acid-base reactions are reactions which occur when we have an acid reacting with a base. Okay. For the purposes of this chapter, acids are any compounds which have a hydrogen ion in them. So ionic type compounds with hydrogen, and bases are any ionic type compounds that have the hydroxide polyatomic ion in them. So, and just to kind of expound on that, so for example, you could see a hydrogen with a polyatomic ion like nitrate or sulfate. That's nitric acid and sulfuric acid, respectively. You guys might recognize those as very strong acids. Additionally, and this might come as a little bit of a surprise, we find that when we put hydrogen with any of our group 7 atoms, so fluorine, chlorine, bromine, iodine, then those form acids as well. Or in other words, they're going to dissociate in solution. Even though they look like covalent type compounds, they will still dissociate really well. So any of our group 7s, look out for those. So this is hydrochloric acid, also known as muriatic acid, strong acid that's used in swimming pools as well as cleaning applications. HBr, same thing, hydrobromic acid. So all of these are acids. You should be able to kind of recognize them by quickly recognizing that you have the hydrogen ion with a polyatomic ion, because you memorized these, so they should kind of jump out at you, or a hydrogen atom with a group 7 ion. And then the bases again have hydroxide. So any metal or polyatomic ion with a hydroxide, for instance, the ammonium polyatomic ion with the hydroxide, that would be a base because you see the hydroxide. Sodium with the hydroxide, base because it's that hydroxide. Magnesium hydroxide even. It's going to be basic. You guys following me here? If I give you something, you could tell me if it's an acid or if it's a base. Need at least one person to say yes. Hopefully 2. Excellent. Okay. And if you have a question, go ahead and type it out. All right. So an acid-base reaction occurs when an acid reacts with a base. So I can just pick any of these acids and react it with any of these bases. So let's pick, for instance, HCl is my acid, and I'm going to react that with my sodium hydroxide as my base. And I'm going to tell you this is a double displacement reaction. So you know that my first cation is going to combine with my second anion, and my second cation is going to combine with my first anion. And I hope that you guys can see that when I do that, I'm going to get this plus this. Does everybody feel comfortable with those predictions for my products of my double displacement reaction there? Yeah, okay, excellent. Now, something interesting here, when I combine H with OH, I could show that as HOH, or what else could I show that as? Yeah, H2O, because I have two hydrogens. So this is what's fancy about acid-base reactions, is that when acids react with bases, I get water and then some sort of salt. Salt is a general term for an ionic compound. So acids, an acid plus a base will give me water and a salt. Here it really is literally like table salt, but would be any other ionic compound would be a salt, metal with a non-metal. This is important and interesting because acids and bases both are nasty things. I mean, they're especially strong ones, they'll dissolve stuff like your skin, like really terrible. But I mean, they're really good for, say, dissolving hard water deposits from your bathtub. So your cleaning solutions might have a weak acid to do that. Or dissolving hair plugs from your drains. So your Drano solution is going to be a really strong basic solution. No, Philip, no, stop. No. Acids and bases both can participate in oxidation reduction reactions, but we're not going anywhere near that. I'm glad that you mentioned that, Philip. Right now we're just doing double displacement and not any oxidation reduction reactions. And so in all of these, there should be no oxidation or reduction that takes place. And you can track that by looking at the charges of each thing, because the charges don't change. And we'll see when we talk about oxidation reduction reactions, that's how you can tell that's occurring. The charge changes. But the charges don't change here. We can just determine what the charge was on this cation and combine it with that anion based on the charge that it was there, and they're exactly the same as they were on the left-hand side. Good, I'm glad that you mentioned that. Anyways, so if you have acids, they'll react with bases, and they give us water, and they give us salt. And so for the purposes of this chapter, you're going to basically need to be able to predict the products of acid-base reactions, like other double displacement reactions, be able to tell me what is an acid and what is a base, and be able to show me the complete ionic equation and net ionic equation. And we're going to do that in just a second after we cover precipitation reactions. But everybody feel pretty good about acid-base reactions just on the surface of it? Kind of. It's okay. We'll do some practice problem. Well, actually, we'll do one more before we go on. Let's pick HBr, and we're gonna combine it with NH4OH. What would be the two products you would expect to see in this double displacement reaction? Water, HOH or H2O, excellent. And perfect. Now, Philip and Robin both said BrNH4, But there's one thing that we need to do there. You're right. There's a right, exactly right, that the H went with the OH and the bromine went with the ammonium. But there's one other thing we have to make sure we do when we report that compound. And that is that when we show ionic compounds, the cation is always listed first, which is why we listed C before B, because we wanted the cation to be listed first. So instead of bromide ammonium, instead of BrNH4, how should I report that? NH4Br. Or ammonium bromide. Does that sound like it? Does that sound nicer? Do you guys feel more comfortable with ammonium bromide? Yeah. You guys kind of were like, bromide ammonium? That seems like it should be. But as soon as you call it ammonium bromide instead, then it sounds right, because that's what you've heard. You've always heard cation before the anion. So perfect. That's exactly right. We made water and ammonium bromide. Well, hang on a second here. Just assume that you're not looking at the list of the stuff that's acids and the stuff that's bases. If I have the HBr and the NH4OH, how do I know which one's which? Yes, I'll show this. I mean, here it was in the list, but what am I looking for? What does everything in those lists have in common? Robin says, look for the H, right? The water is HOH. Good. And the one that donated the H was the acid, and then one that donated the OH, that came from the base. So that H came from the acid, this OH came from the base. So you just come back here and you can say, all right, this one donated the H, so it must have been the acid. And this one donated the OH, so it must have been the base. Excellent, perfect. Okay, so that's acid-base reactions. Again, it's just a double displacement reaction where your two compounds to start happen to be an acid and a base. Okay. All right, so next let's talk about precipitation reactions. And precipitation reactions are double displacement reactions where one of my products doesn't like to dissolve in water and it will fall out of solution. We say it precipitates out of solution because it forms a solid instead of being dissolved in water. So all of the other double displacement reactions we do, including acid bases, we kind of assume will be done in water because HCl is going to come, even the strongest concentration is going to be dissolved in water. Sodium hydroxide usually dissolved in water, although I can get solid pellets. So we put these two water solutions together and we get more water and salt. So it kind of makes a neutral solution. Sometimes we call these neutralization reactions. We're going to go to a lot more depth on acids and bases in chapter 11 or chapter 10. But for the moment, all we need to be able to do is recognize that's my acid, that's my base. I make water, I make salt. So precipitation then, we get, let's see, where did my cursor go? Here we go. Our AB plus CD goes to form AD plus CB. And here we're now worried about what's going to be dissolved in water and what's not. So we'll find in reactions, we're going to put phases in parentheses as subscripts. So we're going to say AB might be aqueous. Aqueous means AQ, stands for aqueous. It means dissolved in water. So I have an aqueous solution of AB and I combine it with an aqueous solution of CD. And maybe I'll get an aqueous solution of AD, but then I'll get a solid solution of CB. If I form a solid, that makes it a precipitation reaction. You guys have heard the term precipitation with respect to rain, like rain falls out of the sky. You can look at it in the same thing. We've got this solid will fall out of the solution and collect on the bottom. Is essentially where you get that term precipitation. So the next question that we have is, how do I know if I put an ionic compound in solution, how do I know if it's going to dissolve or if it's going to be a solid? Philip, that's a great question. Yes, with precipitation reactions, we always assume that water is the part of all your solutions. In other words, you're in water for all of the reaction unless you are a precipitate. So if you have that little s as a subscript, that means that that product or reactant is a solid and not dissolved in the water. All right, so that's the next question. How do I know what's going to be dissolved in water and what's going to be a solid? There is a set of rules that you are going to need to memorize to know which that's going to be. Okay. Now we learned 2 chapters ago. We learned when we talked about ionic compounds that ionic compounds dissolve in water and they dissociate in water. Do you guys remember that? Let's see. Where's our picture here? Ionic compounds. Did we get to draw that little picture? Yeah, here we go. Here's a dissociation. If you remember this from the lecture. When I put an ionic compound in water, not only does it dissolve, but it completely dissociates and splits up. So if it does dissolve, it will dissociate, and if it doesn't dissolve, it'll just be a solid on the bottom. And here's how this is going to be important in just a minute. But here are the rules that you're going to need to know. These come from lecture chapter 6.3, at least the notes that are labeled as such. Really what we'll find is that almost all ionic compounds are soluble. And these are the rules, and we have to go in order. Number 1 trumps number 2, number 2 trumps number 3. So number 1, anything formed with group 1. So if you have hydrogen, sodium, lithium, potassium, or if you have polyatomic ions, ammonium, or nitrate, or acetate, or perchlorate, these are always soluble. In other words, soluble means they will be dissolved or aqueous. They will dissolve, they will dissociate, they will be in aqueous solution. Rule number 2, halides are almost always soluble. The only exceptions we have are if I stick it with silver, mercury, or lead, these specific ions. So halides almost always will dissolve, except in these rare cases. At number 3, compounds with sulfates, again, almost always soluble, except when paired with these ones. These are like kryptonite for sulfates, kryptonite for our halides. Okay. But everything else is soluble, generally speaking, and for the purposes of this class. There are obviously many, many, many ionic compounds out there. If it's not on this list, this should be looked at basically as the list of things that are soluble. If something is not on the list at all, then we're going to say it's not soluble because it's not on our list. So let me just throw a couple of these out at you, and you guys can tell me if they would be soluble or if they would not be soluble. Okay, just for practice. If I had a solution with ammonium nitrate, would that be soluble or not soluble? Soluble. Why? Perfect. Because rule number 1 tells me if I have a compound with ammonium, it's soluble. And if I have a compound with nitrate, it's soluble. So it's like doubly soluble. It's definitely soluble. Excellent. If I have a compound of ammonium hydroxide, would that be soluble or not soluble? And why? Soluble. You guys are exactly right. You're exactly right. Hydroxide is not listed, but ammonium is. And this doesn't just say that ammonium is soluble, it says any compound formed with ammonium is soluble. So you can just see the ammonium and go like, oh, yep, that's on the list. Rule number 1, it's soluble because that's got one part on it that is soluble. All right, let's say we had iron 2 hydroxide. Soluble or not soluble? Jenica says not soluble. Anybody want to second the motion? We vote iron 2 hydroxide not soluble? Or dissenting opinion? Katie H agrees. All right. Why? Why did you say not soluble? Brooks agrees. What are you basing that analysis on? Just so that everybody else can make it too. Perfect. Kitty's exactly right. This is our list of things that are soluble. If I'm not on the list, I'm not soluble. So iron isn't on the list, and hydroxide is not on the list. Since neither are on the list, we're going to make a good guess that this is insoluble, and that would be a solid. Okay, I think you guys can do this. So let's do a practice example of a whole reaction and see if we can guess what happens. Let's take a reaction where we're combining silver nitrate with sodium chloride. We need to do 2 things. We need to do 3 things. First off, we need to be able to tell what my products are going to be. And this is a double displacement, so I think you guys can do that because we always know the outside ions go together, the inside ions go together, right? And second of all, we need to be able to say whether each of the species is soluble or insoluble, so we can label it properly. So what will my products be? Oh, Philip is like, you've been doing your reading. I can tell. You've been working ahead. Okay, so my sodium goes with my nitrate. That was my insides. And my silver goes with my chlorides. That was my outsides. And it's important, these are simple examples where my charge is +1 and -1 and +1 and -1. So that worked really well. But if something would be +2, it would be important to make sure that those charges cancel as well. Okay, so that was step 1, was determining what my products were. And so next we're going to say what of these things are soluble, what are insoluble. So AgNO3, is that soluble or not? Soluble. Okay, so that's going to be AQ, aqueous, means dissolved in water or soluble. But that's because nitrate is on a list of things that are always soluble. Excellent. Number 2, NaCl, soluble, not soluble? Perfect. NaCl, soluble, because compounds formed with chlorine are always soluble unless with these things, but sodium is not listed. Or sorry, the easier thing to say is that sodium, group 1, always soluble. Okay, next, NaNO3, soluble or not soluble? Soluble. Sodium is always soluble. We can just stop right there and say the whole thing's soluble. And finally, AgCl, soluble or not soluble? Not soluble. Why? Because of the silver. Exactly. Because this says halides like chlorine soluble except when paired with silver. Wah, wah. Okay. Not soluble means it's a solid. We're going to put a little S there. Excellent. Good job. Okay, we are out of time, but I'm going to direct you to the ICA 5.1. And we've got parts 2 and 3. This is asking for balanced molecular and net ionic equation. Ignore this for the moment. We'll go over it on Wednesday. I just want you to do a balanced molecular reaction when these are mixed together. So these are all, or mostly, not all of them, mostly precipitation reactions. And these are acid-base reactions. Acid-base reactions. Again, don't worry about the net ionic equation. We'll cover that on Wednesday. I just want you, oh, well, that's easy. These ones you just have to balance because you already have the products. For the precipitation reactions, you have to tell me what the products are, right? Again, outsides and insides together. And well, this should be a typo. That should actually be a 2. That'll make it easier. Should be 2, PbNO3, 2. And note that I can ask this question by naming those compounds, because you guys should know how to give me a formula from a name. So this is just a little bit of practice saying, okay, potassium is K+, carbonate is CO3 2-. So this is K2, CO3, etc., etc. Okay? Practice, because I know you need it, because it showed on the last exam a little bit of that. So nitric acid is HNO3. You don't have to name those. But I do expect you guys will come to class on Wednesday with these done, just the balanced molecular equations, so that we can jump right into net ionic equations. And then we'll cover oxidation reduction, which is just the very last section, section 4, and we'll be done with chapter 5. That'll be it. Just in time for you guys to turn in the homework on Friday. So, any last minute questions before I let y'all go?